Welcome back to DemystifySci. My name's Anastasia,
I'm Shiloh.
and this is the place where we search for the theories and ideas that are going to change the world. Earlier this week, we opened up a conversation with Vortex hydrodynamic ether theorist Dmitry Osinilo, who is a Russian physicist that is trying to come up with a model for how to explain the fundamental phenomena of nature. In the first part of this conversation, published earlier this week, we talked through all of the specific details that you need to make a good theory to explain all of the big mysterious phenomena that surround us: light, electricity, magnetism, gravity. And we got to the very edge of the conversation where we started to talk about the specifics of Osenilo's theory, which is ether hydrodynamics. And in this conversation, we go through the way that he uses his gaseous ether model to solve all of these problems.
So if you haven't heard part one, go back and listen to that one first because it lays the grounds for why we even need such a model in the first place. And of course, go back and check out our series with the various elastic ether theorists so you can compare and contrast the ideas. Meanwhile, we have to keep this project going, and it is entirely paid for by you guys. That means we work directly for you, but we do need you to support the project voluntarily. You can do that primarily by coming over to patreon.com/demystifysci and joining our community there, which is a really, really smart community that we actually meet with once a week, every Sunday morning, and I'd love to see you there. So check it out. You can be part of that community for as little as 75 cents a week, which seems like nothing, but all of these little donations actually do add up to help us keep the lights on, to help us put more and more time into this project and make sure we can bring you better and better material.
You can also support the project in a couple of other ways. We have some merchandise for sale down in the description. Shiloh's actually wearing our Gothian Spectrum shirt. One of the things that we're really trying to do here is we're trying to make sure that the ways in which we support this podcast are integrated. We don't want to sell other people's merchandise. We don't want to sell tchotchkes on the internet or break in the middle of the episode for some kind of long digression into why you should buy some, VPN that lets you gamble on egg futures or something. We really want to be able to offer you a way to support this project in a way that feels clean and clear and cohesive. And so, in addition to the merchandise that we have down in the YouTube shelf below that's clothing, we also have something that I am particularly proud of, which is our record. We have a band called Secretary of Nature, and we just printed vinyl copies of our first record. It's called Everything Is So Good Here. And it kind of lets us do everything that we can't do on the podcast. If you've listened to us for long enough, you know that we have this dualistic view of the world, which is that, yes, when we talk about science and we talk about physics, we have to talk about mechanisms and we have to talk about material bodies interacting. But we're also really aware of the fact that the universe is filled with the ineffable spirit of living beings. And there's no other place to talk about that than in poetry and song and verse and art. And this record is the place where we do that.
And you might be thinking, why in the world should I buy a vinyl record? There's very high quality digital music, including our music, which you can go listen to on Spotify if you want. But think about it, it's become really, really hard for musicians to justify what they do because they have nothing to sell anymore. Nobody's making money off of streaming, right? And so not only is this a really interesting physical representation of the waveforms of the music that we're creating, but it's also a chance for you to support the project and make sure that we have time and energy to dedicate towards that music project going forward. So somebody in your life has a record player, and I'm sure they would love to get a copy of Everything Is So Good Here.
And before we get to the conversation, two more small notes. If you have an idea that you want to share with the world, remember to sign up for the next Paradigm Drift. It is going to be on Friday, March 13th. The details are in the link down in the description. We would love to hear from you if you have some idea that you think is going to change the world. And also, if you want to hear our perspective on how we think that light, gravity, electricity, magnetism, all of the big mysterious phenomena of the world work, then consider picking up a copy of our upcoming book, Paradox Lost: The Material Principles of Natural Philosophy, where we get the chance to lay out exactly how we think all of the greatest mysteries of the universe unfold. In the meantime, enjoy our conversation with Dmitry Osinilo and check out a little sample of our music as we head into the conversation. Thank you, and see you next time. want to understand something, which is that you said transverse waves need surfaces.
Just in solid bodies.
But
In other type of bodies, they don't need surfaces because we have vortex phenomena which can be considered as transverse waves.
Okay, so why do, on a theoretical mechanistic level, why do gases carry transverse waves while solids and fluids don't?
Because gas can move, you can make complex trajectories of gas, and you cannot have complex trajectories in solid bodies because solid body is stationary, it's stable. You can have just oscillations.
Okay, and so inside of a liquid, though, you could, and you said something earlier, which is that the fluidic model in some ways is similar to the
Yeah,
gaseous parameters, and the main difference between a gas and a liquid is interactions between the subunits, right?
just attraction of molecules. Gas molecules don't attract to each other.
Does that make the mathematics of a gaseous ether easier than the mathematics of a fluid ether?
Just more complex, more difficult. Gaseous models are much more difficult because of compression, because compression limits in gaseous much more wide. And there is much more different phenomena in gaseous than in liquids.
Okay, so is the reason that you prefer a gaseous ether to the liquid ether because it can produce more of these complex phenomena?
Yeah, one of the reasons. And because, for example, particles have much more density than fields. Particles have density maybe 10 in 17th orders of magnitude, kilograms divided by cubic meter. And free space have almost zero density. That's why we need something that can be compressed in wide range.
I don't know what these particle thingies you're talking about are.
You made a spread of densities. You have something that's, 10 to the 17 kilograms per meters cubed all the way down.
This is modern scientific consensus that density of protons and neutrons is 10 in 17th order of magnitude. And in my theory, either density is 10 in minus 11 order of magnitude.
Right on. So there's a spread available. That's why you like this. And liquids are generally less compressible. There's less of a spread of density
Yeah.
possible.
And more one, if liquids are much more viscous, and we have a lot of phenomena that have almost no viscosity, and we should describe them too.
What kind of phenomena have almost no viscosity?
For example, light propagates for tens of milliards of years and loses energy very slow. And in modern scientific consensus, light doesn't lose an energy. It
You're
just
talking about redshift or something, right?
yeah, I talk about redshift, and that's one of examples when energy conservation law doesn't work.
Can I ask you a question that's completely off topic? I promise we'll get right back to conservation laws.
Okay.
Do the academic Russians believe in the Big Bang?
Uh, Almost everyone, except
Really?
of my scientific community.
Okay. I'm just checking because yeah, I think. Anyways, it doesn't matter. I just wanted to ask a Russian who was
Actually,
research.
scientific consensus is all over the world things.
Yeah. I just didn't know the Russians are they're on their own island, so to speak.
No, it's not. In this case, they are on the one island.
Okay, okay,
Uh,
just checking. Anyways, yeah, where were we at? Damn it.
conservation.
Conservation, yeah. Yeah.
Conservation law is not okay. Conservation law can be derived just from Newtonian laws. For example, first law of Newton that there is inertial systems is a kind of conservation law, just because it says that there is no movement without an interaction,
Mm.
and that's almost the same thing as energy conservation law. And maybe Newtonian's laws the only thing we need to believe. But it's not a problem because we see that they work every day.
Well, there are strange things about Newton, right? So if you crack open the Principia, the very first thing is that he says, "All right, we're going to define mass as some kind of quantity of matter in some volume. And then he just goes and he does things with mass. Like mass appears in many of his equations. Mass is very important to his laws.
Yeah.
But he begins the book with this assumption that mass just is. He never
Yeah,
explains where it comes from.
I'm totally agree with him.
Okay.
Absolutely agree with him. And there are a lot of theories when scientists try to explain mass.
Mm.
But even if you try to explain inertia of protons and neutrons, you need to have inertia of ether. If you want to explain inertia of ether, you have to have inertia of something else. And that's a bad way to produce scientific results. So, okay, today I cannot understand mass,
Hmm.
but I have mass, I use it, I have a lot of experiments with it, and it works. And that's the only thing we should consider as a priori thing.
But do you think that a full theory of fundamental physics is required to explain where mass comes from?
No, I don't think so. We don't need to explain this before we receive some experimental results that can help us to explain this. Because
Sure, but ideally, at the end of the day, someone's like, why does this have mass? Because, okay, the reason that I think that this is important, and I'll
yeah,
argue for this, is that there's a few key features of physics
mhm,
where mass is disproportionately important.
yeah,
And I think that that's in the equivalence principle. So Einstein, when constructing general relativity, says that F equals ma and F equals m1 m2 over r squared times g are the same F, and so you can set them equal to one another. So this like inertial mass is equivalent to gravitational mass.
yeah.
Inertia and gravity, the same thing.
Yes, but then you have this other weird phenomenon that I think that any theory really has to explain, which is like why do why do things have inertia?
Actually, it's the main question, maybe, but we have no data to answer it.
Okay,
We have
that's fair.
inertia, and Newtonian laws describes how this inertia works. This is the only thing that we should just believe, maybe.
I think it's fine. I think that it's a mystery that needs addressed. I think we can accept that we don't have answers for this, that, or the other thing and move on. Like, it's
Yeah,
not like anyone's ever come on this show and explained in a rational way what mass is. That just hasn't happened yet. So
Yeah.
it's
For
okay.
example, in start of 20th century, we have no explanation for viscosity gases. And now we have, and now we have a theory, either dynamics, and we have a lot of new scientific results. And when we can explain mass, we will explain it.
Mm.
I think it's
Okay.
okay.
Yeah, I mean, so then I guess when we start, go ahead.
Yeah, do you want to pick up on those transverse wave thingies in the gas and all of that? Maybe. I mean, we want to start to understand his theory a bit better.
Yeah, well, I mean, I think that Dima made the case that gases just obviously, apparently, can carry transverse waves. They're capable of these like much more intricate conformations when they are set into motion than liquids because of compressibility, because of these density functions. Gas is the only feature of nature that is able to, that seems even remotely possible to conform to the observed range of densities that have been described, where if you assume that the upper limit of density is this atomic particle in the nucleus, where it's 17 orders of magnitude of kilograms per meters cubed, out in intergalactic space, we're almost at zero. So you need a substance that
Yeah.
works at all of those densities. Okay.
Yes. 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 Of course.
And the reason that I ask about the question of mass is because this very first piece has
Hmm.
mass already in it. And so I'm like, okay, is that something that we can explain? We can set
Actually,
mass.
ether is not very first piece because it's just a new layer of substance. We have abstract substance, then we know that there is solid bodies, liquids, gaseous, and then we understand that there are molecules which are constraining substance. Then we have understood that there are atoms which are bricks of molecules. Then we understood that there are elementary particles which are bricks of atoms. And now we know that there is an ether which is a material of elementary particles. And in the future, we will definitely know that ether consisted from something.
Okay, so one of the properties of gases is that they tend to disperse in the absence of a container. So if you have a balloon and the
Yeah.
balloon is filled with gas
Yeah.
and you pop the balloon, the gas
Yeah.
all moves away from itself and just dissipates into the room.
Yeah.
And then if you
You are
break,
talking about boundaries of universe or something like that. Yeah.
well, I suppose I'm asking the fundamental question of what holds the gas in place so that it doesn't just rarefy progressively.
Actually, imagine you are in a big tank. Okay, tank, and you don't see any walls of it. And you don't see it just because you have no tool to see this. And for now, we can see just to maybe 14 billions of years, light years, and that's all we can see. And maybe these boundaries are much farther than 14 light years away.
That's
But
going to be a crazy headline if that turns out to be the case. Like, they power up the next generation of space telescopes and they see that, like, we're inside of a fish tank or something. Like, oh my God, there's a giant glass wall. And then it's like, oh, okay. Everything makes perfect sense all of a sudden.
Yeah, I
talk
mean it's a
about
hell of an assumption, but at least you've made it.
we have no data, experimental data to talk about boundaries of universe because for now we don't see them. And of course, common sense says us that they are, but we don't know it. And I don't think it's a science question to talk about we don't know and we have no data to start talk about this.
Well, the thing is that it is required for the as a basic uh, prediction of the theory, right?
I mean, one thing that people do all the time in standard molecular simulations is they just assume that they have this horizon that will always keep feeding them new molecules, right? So
Mm.
we do these MD simulations. I was doing them in liquids, but I assume it's the same in gases too. And you just kind of assume that there's some replenishment rate, right? So, in other words, this points at an assumption that there is no boundary to the universe, which is maybe insane and magical. I probably wouldn't defer to it myself, but I think that an argument might be made that if you don't have a boundary at all, then there's no reason to need a container at the same time. I mean, they're almost I meet
Yeah.
people all the time. This is kind of like when you talk to people. Some people are comfortable with eternity. Some people are comfortable with the beginning of the universe. Some people are comfortable with no boundaries on the size of the universe. And some people are like, that's insane. It's a metaphysical divide, once again. But if you do land on the metaphysical divide of, I don't need a boundary to the universe for it to make sense to me, then you get away from this gas container problem.
Where basically there's just a constant, the rate of influx and efflux of the gas from any area of the universe is constant, and so there's no great loss because it's always being replenished.
Yeah, I don't like it personally, but
But
that
that would be the assumption. Okay, that's fine. I'm content with that. So then I guess the next question is, where do the forms come from?
atoms? What's an atom?
Yeah, what's an atom in this
Um,
theory?
we have protons and neutrons, which are considered as toroidal vortices. And toroidal vortices are attracted by each other. And we can describe this by nuclear forces, by gravitational forces, electromagnetic forces, and these forces, as modern scientific consensus says, collects this nuclei to one bunch of protons and neutrons. And almost the same thing says ether dynamics. But we have mechanical model of this, of all of these interactions. And we have much more precise models of atoms. For example, I almost know how looks like uranium atom and why it decays.
Sounds like you're saying that the nucleus is a vorticular structure, which I assume results because it's the best way to dissipate the pressure that's converging on this point, right? The atom is a point where there's a lot of pressure. The vortex is the most efficient way to dissipate that pressure.
Yeah.
Does that mean, what does that say if the nucleus is like this vortex? What is the shell, the thing that we call the electron shell in chemistry?
It's just linked vortices. So you have intense vortex inside of atom, and you have linked vortex of less density around. And you have electromagnetic fields, you have chemical things, you have maybe van der Waals forces or something like that. And all of these forces are different types of motion processes.
Do you have a picture of this like vortex of vortices that you treat the simplest atom as? Like, do you have a picture of a hydrogen?
A picture of hydrogen is just kind of one toroidal vortex. And Hill's vortices describes kind of hydrogen atom.
Okay, so I have a question about this.
Okay.
The were you gonna say something, Shay? Shayla's deep in thought. His brow is furrowed.
I just look like this. I'm really a nice guy. Everybody says I look really mean, but I'm not mean, I promise. I just think this is when I'm thinking really hard. I'm trying to concentrate, but I just look evil for some reason.
It's because he's looking for the weak point in the argument to attack it. It's the art of war. Okay, so the Schrödinger wave equation gives orbital shapes. Like, it gives probability functions for what atom.
The spatial distribution.
Say it again?
The spatial distribution of the wave.
Yes. And the simplest, and all of these are spherical harmonics of hydrogen.
Yeah, understood.
And the simplest one is just hydrogen in its ground state, and it is spherical. It is not toroidal.
Depends.
Actually, you are saying about symmetry of, for example, electric field of hydrogen atom. And we have no experiments which can confirm this. Some atoms have no spherical symmetry. There are a lot of experiments and consider magnetic moment. You have a magnetic field which rotates atom. How can it be spherical? How can it have spherical symmetry if it rotates and it not indifferent to magnetic field? So it has something that is not symmetrical, obviously, and but it has excess. And if we consider atoms as vortices, we will definitely have excess.
And the axis could be precessing or tumbling. It's hard to temporally resolve that, right? So you imagine you're doing an experiment and you're looking for the axis of the hydrogen, but it's got thermal motion. It's kind of just bouncing all over the place.
It's
on average, it might look like a sphere to you in your experiment.
It's not all, because if you have some electric field and you apply it to hydrogen atom, it will rotate to compensate the pressure. And when you try to measure it, you will always receive the same result because it rotates by electric field or magnetic field. So you have no way to measure by this experiment non-spherical symmetry of hydrogen atom.
So basically, it is a convenient approximation that likely obscures some. Is this topology? Or geometry? Like, what is the name for this feature? Is it?
Topology geometry, it's okay. For example, I've said about spin, and everything that describes spin is about topology. It's pretty hard science, but it can be calculated and it can be imagined for now, maybe a week ago.
That's good. That's good. So basically, it's like the topological reality of the hydrogen is
Yeah.
probably more complicated than just this dumb sphere.
Yeah,
And
it's obviously.
magnetism, like its functional relationship to stimuli would suggest that it does have an axis, and there is some polarity to the whole thing. And
Yeah.
yeah, I think that the spherical thing is just a smoothing out. There's also, if you do the like shell deconvolution, the radial distribution function, you end up with something that could also be drawn in a toroidal structure as well, right? It's just when you're, it's just that the sphere is perhaps the smoothest way of putting it, right? You're kind of averaging out all those microstates. I don't know. It was a great
I think
question.
it's a story about spherical horse in vacuum.
Mm,
It's
it-
just a good way to describe some phenomena.
wait, in Russian, do you say the spherical horse?
I think it's a citation of Big Bang Theory.
I think in I've always heard spherical cow.
Spherical horse is a good one too.
I love it. The Russians love their horse metaphors.
I have a question.
Tell us.
Is there any gas system, experimental gas system, that reproduces this standing toroidal vortex that we've been talking around with the hydrogen?
First of all, Hill's vortex is the old work of early stages of hydrodynamics. And the Hill vortex is describing just a toroidal vortex moving in space, in liquid. And that's the one thing. And there are a lot of different experiments when you have toroidal vortices. For example, Wood's box. You have a box, you have a hole, and membrane on the side. You can slap this and you will have a toroidal vortex. And there are everywhere vortices. And most of them are invisible because it's not too intense to be visible. But if you have smoke, you will definitely see it.
So the vortex structures that you've pointed to now, they all dissipate very quickly, right?
It depends. Imagine you have not 10 fifth orders of magnitude pressure in air, but 36 orders of magnitude pressure in ether. So you have 31 orders difference in pressure and in time of life, for example. That's one way. Another way, density of air is kind of 1 kilogram per cubic meter. And density of an ether is minus 10 order of magnitude. So you have much less viscosity of ether. So all these orders of magnitude adding time of living of particles.
Okay, so does that suggest that there's a there's a lifetime to something that's even as simple as a hydrogen atom, where there's material properties of the vortex, where there's some kind of impulse that produces
Yeah.
the vortex, and then because so you said something really interesting where you're like as you increase the pressure by 30 orders of magnitude, you extend the life of the vortex
Yes.
commensurately by the same 30 orders of magnitude or some.
It's just not assumption. It's rude calculation for
Sure,
kind of
back of
yeah.
the envelope, like just kind of rough calculus.
Rough
But
calculus, yes.
if we assume that there is a lifetime,
Mhm.
does that imply, because I always thought of something like a hydrogen as being eternal, but it seems like your theory suggests that it has a lifetime.
Yeah, it has a lifetime, of course. Everything in our universe has a lifetime, but um, we have an experiment that says that hydrogen atoms does not decay. But imagine you have you have a bunch of young men which are sportsmen and which are pretty in good shape, and you let them to live for maybe 2 weeks, and after these 2 weeks no one died. Then you will make a conclusion that people doesn't die. That's why protons doesn't decay, because we have just young protons, because they were born in maybe a center of black holes or in Earth, under the Earth's surface, and all of them are pretty young. That's why we have no destruction experiments of protons and neutrons.
Okay.
It's but the time of living of protons maybe tens or more billions of years.
All right, let's talk about light a little bit. So,
Yeah.
what is happening when an atom shoots off a photon?
I have a question.
Oh, it's
Do you want to do light first, or do you want to do charge and electricity first? Because don't we need that in order for light?
This is kind of uh, which do you need more to make the ox cart go, the ox or the cart?
Okay, let's do light. Let's do light.
Yeah, I don't know. Maybe one will inform the other. It doesn't really matter. I agree.
But
It could go either way.
okay, let's do light.
I was just looking at our outline here.
Thank God we have that.
We've also mentioned that photons are vortexes so I thought maybe I would try
Okay,
to make a
fantastic.
picture of this a little bit.
Okay, let's do it.
actually my model of photons meet a lot of resistance, because maybe it's new or it's not already known before me and before Atsukovsky, which started hydrodynamics. But I think photons are Kalman vortices. You can see these type of vortices in, for example, when the boat is sailing on water surface, and behind the boat will be carbon vortex street. And
What is that word you say?
It's Karman vortex. I'm trying to find. I'm trying to find a
carbon
picture.
vortex street.
Street?
Street, I guess it's street.
That
And
sounds like a weird
Yeah, it
indie
is
rock
Karman
band or something.
vortex street. Oh, okay. So in the wake of a boat, as you're traveling, there's these little whirls that form behind it as you
actually,
go.
it's pairs of circular vortices which are rotating to opposite directions.
Okay, I'll add
And
a picture of that here because that's I think
Yeah,
a
these are
great visual.
beautiful. Yeah, we see these in the rings of Saturn too, I believe. They're everywhere.
we have not a lot of ways to emit light. We have to heat something. We have LEDs, which are used to produce light by conducting current. We can destroy crystals, and we will have some short lights. And
Don't forget about antennas, my favorite.
light and electromagnetic waves are not the same thing.
You
I
told me
beg to
this.
differ.
Okay, we'll fight this out at the
No,
end.
let's do it now.
Right now? Okay.
We're never
all
gonna
right.
come back to it. What? No, it's changed my mind.
Actually, this is just experimental data, because if you want to produce infrared light, then you have to heat something. You have absolutely different ways to produce light instead of producing electromagnetic waves.
The electromagnetic waves that come from an antenna
Mhm.
are, let's say, the like radio frequency, microwave frequency. So they're slower than visible light.
Slow might not be the right word.
Not slower, less.
So their
have
wavelengths are
less.
longer. Their wavelengths are longer.
Yeah, yeah.
They have okay.
But
They have.
that's
So when I
not
say
the
slower,
only.
I'm thinking in the frequency domain. They definitely have a lower frequency. Obviously, lower frequency means slower. I don't know how people.
Actually,
It just makes it sound like the light's moving slower. So I
No, no, no.
understand you. Keep going though.
Okay.
Keep going. Keep
So
going.
like the oscillation that produces the light has to take more time. That's what I mean when I
Okay.
say slower.
yeah.
Okay.
But we have different ways to produce light and electromagnetic fields.
Pardon the interruption, but I have to ask you for a favor. If you were listening to this podcast and you were enjoying it and you want to see more of these ideas in the world and you want to power our ability to explore these ideas in person, to bring listeners together for in-person events, then consider coming over to patreon.com/DemystifySci. For 75 cents a week, you will spare us forever the indignity of having to hawk cheap trinkets on the internet in order to support our podcast. So come over today to patreon.com/DemystifySci and support what you love.
Not only the light, I mean photon structures. For example, X-rays looks like photon structures, for example. And infrared or ultraviolet light is photon structures too. But if we want to describe radio, I think it's not photon things. It's things of a different nature. There is a range when we cannot produce light nor electromagnetic waves. It's maybe 1 terahertz. We have absolutely insane things to make electromagnetic waves in that range. And we have no experiments which can find a link between light and electromagnetic waves in that range.
Okay, so we can make the case for why they're the same thing, but we're making the case in our book, and I think that we should talk about it once we have it laid out. Because I hear what you're saying. You're basically saying that like the behavior of things that are long wavelength electromagnetic disturbances of the field behave so differently from visible light. And there's also this gap in engineering where we have a very hard time producing waves in this frequency range
Yeah.
that makes you suspect that there's actually some kind of true rupture in the phenomena, where on one side of this range you have like true light, which is photons. On the other side of the fracture, you have something else that
Yeah.
is still electromagnetic radiation, but is not like photonic. Like, what's the.
Yeah, it can be described by electromagnetic theory, but it's absolutely different phenomenon.
Look.
Okay.
Yeah, do you have can you tell us the two different mechanisms? Yeah. So what's up with the two different types? Like what can you explain them to me in your theory?
Okay.
Deep sigh.
We can start with photons, the short
Yeah.
wavelength stuff, right?
Hold on. Before we do that, I have a question. So is everything above visible light the same thing? Or is there a similar break for you once you start to get into like X-rays and gamma rays where they're also not light?
I think X-rays and gamma rays are also light, are also photon structures, because they behave like light. And there is not only experimental but theoretic difference between them, because for calculate light, you should use optic electromagnetic constant. And if you want to calculate electromagnetic field, you should use electromagnetic constant. This maybe 80 instead of 1.7.
I, like, surprisingly to myself, understand what Dima's trying to say. Dima's basically, and I think that the way that you and I understand the way that light is produced in the radio spectrum versus the visible spectrum kind of also supports this, which is that it appears that the way that light is produced at these longer wavelengths is best described by slightly different mathematics than when you get into the visible spectrum and beyond.
Yeah.
And I think that that has a consequence that is downstream of the way that antennas work, which is they work by forcing ensembles of atoms to perform actions, as opposed to deriving light from the action of a single atom. And so when you get really short wavelength light, I think that's the action of one atom. But if you're
the size of a light is microns, and the size of atom is minus 10 order of magnitude. It's much less, much lower size. So
Sure.
I don't think one atom is enough to emit a light.
Okay, so how do you make sense of like atomic spectra?
Yeah, why don't we just
Uh,
get his model of... I haven't got his model of light yet.
Okay, let's
This
get
is
that.
getting confusing. Cause like maybe we can just talk about your model of light and then your model of radio waves, and then either move
radio
on or
waves.
glue them together.
Yeah, because we got to this Kármán vortex.
Yeah.
So you're like, people
So
don't agree with your model of light because the Kármán vortex, and then we went off the
yeah,
cliff.
okay. When you heat in a substance, it moves faster, and the vortex is emitting some flows. And these flows flow around another atoms. And when they flow around, they emit these Kármán vortices. And this is photons. When you try to emit electromagnetic waves, you don't need all this. You just need a motion in wires.
Wait, hold on
And
1 second. I want to make sure. Do you understand his model of light? So it's like a wind going past an atom. Is that what you're saying?
something like that, yes.
And so the atom isn't the source of the wind.
One atom emits flows, and another atom is obstacle to this flow. And when you have this flowing around another atom, you have Kármán vortices, and then they goes away and fly billions of years.
Okay, does that make sense to you?
And what happens when the Kármán streets hit your eyeball or hit the telescope billions of years away? What is...
Just interaction. So you have some little balls that colliding with your physical tools to receive these balls, and because it has frequency, you will have some resonance frequencies in your eyeballs, and that's why one kind of receptors on in your eye will receive blue light, and the other receptors will receive green light.
What about with a mirror or something like that?
Just reflecting kind of a ball which is colliding with a wall and goes opposite side.
Why would the Kármán vortices reflect off of a wall?
I think in either vortices are much more stable than in air, and it corresponds to pressure, density, and other things. And we have just colliding of physical objects.
So it sounds basically what Dima is saying is that the density of the ether is such that the vortices are sufficiently robust that
Yeah,
when they hit a surface,
yeah,
that they're able to be maintained more or less as like the vortex is maintained. It basically behaves like a body. And the
yeah.
vortex itself, this like total collection of ether particles in this vorticular motion bounces off the surface and continues along the trajectory because this is a necessary assumption.
But it doesn't do that sometimes, like with the eyeball?
No, in that sense, well, that's the difference between a reflective surface and an absorbent surface. A reflective
That's the
surface
question.
is, I guess the question is, what are the properties of the surface that makes it either absorb the Kármán vortex or reflect it?
I think it's work in progress question.
Okay, that's fair.
No worries.
Yeah, I mean,
Let's, all right, so then in the radio frequency domain, how is it different?
Actually, you have a big surface on which ether flows propagates, and entrains either near of this and make different flows. And if you have antenna of complex form or complex shape, you will receive different shapes of electromagnetic fields. That's why some antennas works good, some antenna works bad because they have different shapes, and sometimes shape of a wave doesn't fit to shape of antenna.
Hmm. Mm.
It's just viscosity processes in either.
I mean, I can see what you're saying. I think that by virtue of how you have constructed this model, it is a natural consequence of your model of the photon.
Actually, photons were described after electromagnetic fields are described by hydrodynamics. For example,
But this is the Kármán street vortex is your model of photons, right?
it's not really my model because first it was the model of Atsukovsky, Vladimir Akimовich, who invented the hydrodynamics maybe 60 years ago. But he has not a lot of computational powers. He has no internet in my volume, and he has no AI, and I
Yeah.
have it.
It could
And
be a blessing or a curse.
Exactly. We get a lot of AI psychosis emails these days. Um,
oh yeah, I know.
you as well?
Yeah. Be careful
Kind of.
making friends with robots, kids. It's probably just stick to the drugs instead, maybe. Um, okay, okay. I think yeah, we can just let's look at gravity or something.
Well,
All right, we're not done. We're gonna go
no,
deeper.
no, no, because like, what is light? Light is,
You mean
and
electromagnetic radiation?
that's what I mean. Like light.
Kind of electromagnetic radiations, yes.
Okay, do you treat the photon as being an electromagnetic oscillation?
Uh, what do you mean by saying oscillation? It's like this type of motion.
Well, I mean, the model that we have for light is that it is a transverse wave
Yeah,
with electric field oscillating in one direction, magnetic field
yeah.
oscillating in the other direction, and both of them are perpendicular to the direction of the rays travel. That's like
Uh,
if you open up a textbook, if you open up Wikipedia, it like this is the universal description for like all of the electromagnetic spectrum. That it is this kind of disturbance,
It's also a radial disturbance too, which complicates the hell out
which
of the
is
whole
like the
thing.
circular polarization.
No, it goes in every direction from the point source.
Yes. So like that like um
So there's a lot of these Carmen streets everywhere.
yeah, it's true.
yeah. Ah, well, so that's really interesting because like in a two atom universe where you just have one photon, well, hold on. That's sorry. I'll set that aside. Okay. So do you think that that representation is incorrect? Do you think that it only applies to certain types of photons?
Certain types of electromagnetic radiation.
Certain types of electromagnetic radiation? Like that's the piece that I'm trying to like slot in because I'm like I can accept that it's Kármán vortices. I can accept that I hear what you're saying about the difference in the
By accept, do you mean
phenomenon.
you can understand?
Yeah, like I'm just like this is Dima's model. Like I'm not gonna I would
Just trying to understand you.
yeah, yeah, yeah. And so
Actually,
okay.
electromagnetic is general theory of flows, and everything we can describe by flows is can be described by electromagnetism.
Sure, but we
Most
also
equations.
like if you take an antenna
Mhm.
and you oscillate current in it, you take a wire and
Yeah,
you put alternating current through it,
yeah,
you produce radio waves. Very, very
yeah.
low frequency, but radio waves.
It's huge vortices.
Yes. So
Yeah.
the description of those waves is that 60 cycles a second of the
Mhm.
electric field pointing in one direction, then it points in the other direction. And that's the
Mhm.
oscillation we're talking about. And that's also the oscillation that happens inside the wire. And the question that I'm trying to ask is when you talk about visible light being different than that, what do you mean exactly in terms of that picture of light, electromagnetic radiation, being a periodic oscillation of electric and magnetic action along a path of travel?
I should describe electromagnetic terms before we can talk about this. Actually,
We've resolved if the ox or the cart had to go first.
okay. Uh, Before we
Whichever one you
talk,
start with, you're always
Yeah, that's true.
you're always screwed. Okay, no, let's do electricity and magnetism.
before we talk about what electricity is, we should, as we tried before, observe phenomena of electromagnetism. And maybe what we know, electromagnetism is generated by and absorbed by material bodies. So you have antenna, you have heated body or something like that. And when light or electromagnetic fields propagates through the space, it is faded out very slowly. And for example, visible light makes his frequency lower, maybe for 10 billion years. And that's why we should consider that ether has low viscosity, but it has viscosity because light is fading out.
So when you say fading out, do you mean that the frequency is decreasing, or do you mean that the brightness is decreasing?
I mean energy lowers.
Okay,
Of
so
light.
the
So
redshift.
frequency, yes. For example, redshift, but we have, for example, blue shift, and it will be described maybe later if we have a time. So we have viscosity, and we should consider hydrodynamic equations with viscosity. And when I assumed that viscosity exists in ether, then I derived Maxwell's equations by hydrodynamics. It's just Navier-Stokes equations and some linearization, some simplification, and then we have hydrodynamic equations, absolutely the same equations like Maxwell's, and it's strict derivation. So we should consider charges as sources of electromagnetic fields or currents as sources of electromagnetic fields. And this interaction with free ether is made by viscosity. And if we assume this, if we try to calculate this, then we receive that magnetic field is rotation of ether. And electric field is pressure gradient or acceleration of ether. And then we will receive understandable terms to describe electromagnetic fields in your imagination. And for example, electromagnetic fields are just kind of toroidal vortices, but much lesser density than protons and neutrons. And lights are circular vortices because we receive them in absolutely different conditions. But for describing lights and electromagnetism, we don't need to assume that there are different phenomena because they are described by the same theory. For example, vector potential is just a speed of ether flow, but with the coefficient. And scalar potential is just the kind of pressure divided by density of ether. And we have pretty mechanical descriptions for every electromagnetic phenomena.
So let me get this straight. I want to make sure that I'm following you first before we keep going. So in a wire, just a single wire, the flow of charge to you in this wire, as it's normally stated, that is a diffusion of speed pressure. There's the ether is moving faster in say the minus charge side versus the plus side.
We have
it's diffusion of speed.
No, it's not about diffusion. So imagine toroidal vortex. It has this rotation and this rotation. And if this rotation relative to this rotation in that side, this is charge of one sign. And another side, this is the second sign of charge.
Minus one.
For example, minus one.
So the directionality of it.
Yeah, relative directionality.
Yeah.
So if you rotate it, relative direction will not be changed. When you have a current through the wire. These toroidal vortices are rotating, and they have rotation around wires. And these rotations creates fields, and all we observe.
Magnetic fields.
Magnetic fields, yes. If
And
we have
the electric field is the
electric fields,
tubular rotation? I don't
No,
understand.
it's the forward rotation. So it's like it's a pressure. It's the
Yeah.
dissipation of pressure. There's pressure of the
pressure.
ether at the source, and a deficit of ether at the sink. And so the electric motion is the flow of ether along the wire from high pressure to low pressure.
It's acceleration of
Acceleration.
acceleration or pressure gradient. I should describe this. We have some forces which are produced by Navier-Stokes equations, and we can divide it just mathematically. Divide on vortex things and flow things. And vortex part is magnetic field, and flow part is electric field.
Okay, I
And
think that makes sense. Do you follow?
I think so, yeah. It's like the longitudinal component is the electric field and the rotational
I
portion
don't
is the
think it's
magnetic.
truly longitudinal because it's maybe hydrodynamics is not obvious in many cases. For example,
Well, it's going down the wire, I guess, as opposed to around the wire.
Actually, around the wire we have circle vortices around the wire.
Magnetism.
Yeah, it's magnetism, and we have pressure difference going away from the wire, and it can be described as electric field. But maybe I can't explain it clearly. But magnetic field is just a rotation about around the wires. If you change magnetic field, you will change these rotations, and it will change motion mode, and you will have some density deviations, and it will create something that we can describe as electric field.
I mean, I think that doesn't that make it a little more complicated than it needs to be? Because like if you have a toroidal vortex, you have a fixed relationship between the equatorial rotation and the longitudinal rotation. They're always 90 degrees to each other.
Actually, you can consider it as separated, but you have only one flow. So if
Yes.
you are near the vortex, you can separate them. And if you are far away from this vortex, every flow will be combined and mixed. So you
Sure.
cannot really separate them.
I guess it seems to me that it's not it's hard for me to imagine a condition where the whole thing rotates together, right? Like the torus rotates as a unit.
Mm,
Like in the sense that like for every given equatorial rotation, there's some amount of involution. And there's some constant relationship between the amount it involutes and the amount that it rotates.
yeah,
Right?
yeah.
Like that's just a feature of the torus. And so it's hard to say that like the magnetic field causes the electric field or the electric field causes the magnetic field. It's like, no, this is a consequence of the motion of the torus.
Yes, you're absolutely right. It's hard to explain in fingers, but
Yes.
you can
Yes.
kind of feel this, feel it.
Yeah. And so it makes sense for me that what you're discussing in the wire is that there's some component of the involution of the torus
Mhm.
that is the electric field, and the magnetic field is the perpendicular component. And that electric field has some kind of momentum, it has some kind of vector for its motion, which is down the wire towards the other terminal of your battery or your whatever.
Do you remember Magnus effect? with a rotating ball.
Yes.
And if you want to describe this rotation ball flows around these rotation balls, you will be in difficult situation because it's not obvious. But you can easily calculate the forces which are applied to this ball. And the same thing with electromagnetic field, because when Faraday, Maxwell, and other people invented electromagnetic field, they used interaction with charges. They didn't introduce the magnetic field as a self phenomenon. It is an interaction between some phenomena.
They don't treat magnetism as primary.
Yeah. And,
but it is primary.
No, it isn't.
It isn't.
We can describe flows in terms of magnetic and electric fields.
Yes.
Actually, it's not a real magnetic and electric field because electric field is has two components. For example, vector potential and scalar potential. And always when we are trying to calculate this, we consider electric field is consisted by two components. And we can make kind of Maxwell's equations without simplifications that I did. And we will receive much more components of these fields. But we need to do this work. And for now, it is considered that magnetic fields is rotational things and electric field is maybe laminar flows things.
Okay. I mean, I think that makes sense. Do you want to do gravity, Shiloh?
Yeah, let's talk about gravity. I think we're closely to the same page on this.
The deep specifics of these things are hard to like you said, they're hard to explain on your fingers.
Yeah.
Like and so I think that I understand what you're trying to say about the geometry of the torus and the way that it moves and the effects that has. And I think I agree that that's the correct direction for understanding these pieces. So let's do gravity. Because that's kind of the
How does
last
gravity
piece.
work, Dima?
Okay. First of all, gravity is a thermo-diffusion effect. Where this thermo-diffusion effect comes from? When we have toroidal vortex, we have volume inside this vortex near the axis, and we have much more pressure, much more density in this region. And we have external part of this vortex, and the pressure and density of either much lower. And when either moves inside the torus, it expands and it compresses periodically. And when it expands, it cools down, and when it compresses, it is heated up. And this process absorbs thermal energy or something like that from the ether. And when we absorb an energy from the ether, we have a pressure difference, pressure deviation. And this pressure deviation, if we calculate this, will be the same as Newton said when he invented gravitational theory.
So basically, the atoms are cooling down the ether. Is that a fair way of thinking about it? I mean, they're kind of slowing things down locally because they have this compressor at their heart that is essentially just bringing things to a standstill.
Actually, protons and neutrons consumes thermal energy of ether, but they makes flows around these particles, and flows are considered as electromagnetic or nuclear forces, and heat consumption is considered as gravity. And it is the same process, the unified model, which produces all these interactions. And when I tried to find parameters of either, which can produce all of this, I've received consistent values of them. So this model can explain everything we observe, and it has no contradictions or some kind of 120 orders of magnitude difference deviations between quantum mechanics and relativity. And it's fun because 120 orders of magnitude, it's nonsense. It's not a theory difference. It's just paradox. And in ether dynamics, there is nothing like that. We have absolutely consistent parameters of either.
What are some open questions in your research right now as you work into the future? What are some of the mysteries that you hope to be able to solve?
Maybe the main thing that is observed but is not have no clear explanation is quantum entanglement.
Mm.
Because I have some assumptions, and the main of them is just dirty experiments. Because we have some methodology problems in experiments with quantum entanglement, but it's maybe it's not good explanation. So I'm working on it, and we have a lot of. That's all about quantum entanglement, and we have a lot of experiments which are obtained by either dynamics models. So, for example, longitudinal waves in ether. The speed of longitudinal waves propagation is 23 orders of magnitude meters per second. And it's much faster than light. So we can try to measure it with some experiments. But we already have this. I think there are a lot of experiments with bacteria which receives not light, I think some signal from sun which is received much before the light come to the earth.
Hmm.
So actually Laplace made his work, and he know that gravitational speed is much faster than light. He said that it is 50 million times faster. And then Van Flandern made this similar experiments, and he found that speed of gravity is 11 orders of magnitude faster. And in ether dynamics, we have calculated that the speed of gravity maybe 15 orders faster than light. And it's just lower boundary, because it based on particle experiments, and it's can be not the most fastest value we can obtain from different phenomena.
Are there any other big pieces?
Um, there are a lot of big pieces, I guess, because for example, as I said before, we can not make some simplifications of hydrodynamics and derive flow equations not similar to Maxwell's equations. And we can obtain a lot of different phenomena, different types of antennas or types of light sources. And it's a big field of experimental work. And actually, when you can imagine what do you working on, you can make a lot of assumptions which can be realized in experimental constructions.
Right on, man. Well, do you have a place where people can read all of the details of your work? Do you have a website you could tell people about before we let you go?
Yes, but it's mostly in Russian. But I have started publish on a medium, but it's popular papers, and I have some works on Zenoda, but it's purely scientific papers.
And those are Russian or English?
Zenoda and medium is in English,
Okay.
and I have a lot of Russian sources: Zen, YouTube, maybe Boosty, Live Journal, and others.
The Russians, I think, are the only people still left on LiveJournal.
We have some American.
Russians.
No, not Russians. So we have some American people who doesn't speak Russian, but there are a lot of tools to understand Russian speech by translate it and even write when you watching YouTube.
You also have a podcast.
YouTube Osenilo,
Mm-hmm.
Osenilo podcast, and we have every weekly streams in Russian, and we have on the same channel seminars in near physics faculty of MSU, where a lot of doctors or postdocs tells about their successes in scientific investigations.
That's very cool.
Yeah, it's cool. I think YouTube's getting much better. They're really working towards being able to have auto translate features, and I'm sure it'll eventually go to auto voiceovers. Like, it's all coming down the pipe any day now. We've gotten a few notes about this, and yeah,
I
so
hope
I
this
wouldn't
will
worry
be
about the language
developed
barrier.
soon.
Yeah,
Yeah.
yeah. Well, this is one of the non-pathological uses of AI. I think that'll be really nice.
Maybe.
You can develop AI psychosis in all the language of the world, all the languages of the world.
Fantastic.
Mm-hmm.
All right, Dima. Well, thank you for giving us your time and presenting these ideas. We will add them to our library of ether theorists. It just occurred to me as this was happening, this was the first person who had presented a more traditional ether idea, and everybody else has been on these more like elastic, solid ticks, and
I
yeah,
think that it's probably in some ways, the most complete one that we've encountered, because most people who are working on ether theories don't have an explanation for charge. They don't have subunits really in their models. I think that their simulations are somehow slightly less detailed when they're thinking about these things. And so I think that I think you're probably the farthest along of anybody that we've talked to.
I think it'd be really fun, actually. Maybe we can find a way to get you in a conversation with somebody who has a very different perspective on the ether. I thought
I
that'd
have a
be
lot
really
of
fun.
I had a lot of discussions with authors of different theories, and I am pretty confident that I can explain that they are wrong in some cases,
That sounds fun.
and I will explain why.
I think that could be really fun. I've said before that what we're trying to do here is we're trying to put together a library of what these ideas look like. And
Yeah.
it's been really good to get a sense of how you're thinking about all of these things.
Yeah.
Even if the only outcome is that it gives some spark of inspiration to someone else, it was very much worth it. But I think people
Yeah.
will really enjoy the conversation.
I have enjoyed the conversation.
Excellent. That's good.
All right, man. Well, I hope we didn't keep you up too late. I hope
Thanks.
you sleep well, and yeah, we'll be in touch. Thank you so much.
Yeah, we'll send you a book when it's done. Another couple weeks.
We'll keep talking.
Yeah.
Okay.
All right.
I
Thank you,
can
Dima.
give you my book in paper.
Oh, cool.
We'd love it.
Yeah, we can
Okay.
do a book trade. That'd be great.
Great. Thank you.
All right.
See
Good
ya.
night.
Thanks, Dima.
Take care,
Bye.
Dima. Bye, everybody.